All right, good afternoon, everyone. Welcome to class today. I trust I'll be teaching quite a few young persons today. All right, as we seek to navigate the rest of this module. All right, today we are going to be focusing on generation planning and management. Looking at, load dynamics, talk a little about generation dispatch. Well, that's really the third thing that we look at. So after we look at load dynamics, we'll then talk a little about reserve margin and just how we manage load and generation on the system. Before I go any further, however, I'm just going to comment a little about the work we did last week, because that will represent, or what we did up to last week will represent what will be reflected on your mid-sessional exam, which comes up in 2 weeks, or just about 2 weeks. So the question was about which of the parameters, or coefficients rather, should be used depending on the direction you're going. Now, I'm not going to give a straight answer. Well, that's nothing new, but I'm not going to give a straight answer. Suffice it to say that what I want you to focus on, students, it's not trying to remember which parameter to use, but understand or appreciate the fact that reflection and refraction of a wave occurs where there is a point of discontinuity. In other words, at the point where two media are connected. So if I am moving from the line going towards the cable, then at the line cable junction, I'm going to have reflection, which would therefore be the reflection coefficient based on the line to the cable, because the signal is in the line heading to the cable. At the same time, the refraction or transmission will also be based on the line to the cable, because again, the signal originated in the line and it is heading towards the cable. Now let's think of the signal which is now transmitted. The signal having been transmitted is now in the cable. So if it is moving towards the load, then at the point of discontinuity, or in other words, where the load is connected to the cable, reflection will be based on the cable to load, and refraction would be cable to load. All right? So I want you to, just bear that in mind, that the reflection and refraction occurs at the point of discontinuity. And you focus on where the signal is coming from and where it is going. I hope you can look back at this and at the recording and refresh your mind on that statement. But I don't think I can make it any clearer than what I have said. So let's get into today's lecture. All right, so we're talking about generation planning and management. And we just want to make some general statements up front. And just hopefully we can appreciate some of the fundamental principles for an electrical power system. All right, what is it there for? What are the main objectives of that power system? All right. Or should I say the main objective of the system? And that is to move electrical power or electrical energy to customers. So we want to get the energy, the electrical energy that is generated. We want to get it to the customers, the people who are consuming it. All right? But you want to do so in a safe manner. And of course, that's where your protection and your protection comes in. You want to do so and ensure that it's of acceptable quality, right? And quality here speaks of, issues relating to frequency, voltage levels. For example, you would have set your tolerance at bus bars to be 5%. That's a standard that is used within the industry, that the voltage should not vary outside of that threshold. As it relates to frequency, there are many pieces of equipment that we use that are dependent on time, and that time would be based on the frequency that it is supplied with. And so if you have, for example, a stove with a clock that is supposed to be operating on 60 hertz, and you're trying to use that stove in the Jamaican system, which of course you all know by now is a 50 hertz system, and you are seeking to use the time on that stove to time your baking, then you're gonna have a problem. No, that is a clear issue where timing is concerned. But if you also have, speaking of quality, if you have a stove that is whose timer is based on 50 hertz, and you come and plug it into a Jamaican system where the quality is not that good, meaning that you have the frequency sometimes over 50 hertz, and sometimes it is under, then again, although you have the right equipment in terms of your timer, you're gonna have issues. All right, so you may end up with the thing being too long, or you're taking it out too quickly. Other equipment that you can readily think of, your microwave, your alarm clock. If we have issues with frequency, it's going to drop a few minutes over time, or it's going to speed up over time. Reliability. The thing about a power system is that when we think of its operation, it hardly breaks down, is a better word. However, you want to ensure that, well, the customer has certain expectations. He or she expects that when they go in and flick that switch, that they expect light. And as the provider, you want to ensure that that is the case. All right. So whilst we may not have issues occurring on the system frequently, the expectation of the customer is that when they need power, it must be available. It must be reliable. All right. And then, of course, as I've said, with not just power systems, but engineering in general, our objective and your purpose for signing up at this university and now sitting, listening to me, spending all this money at this institution, becoming engineers, is that you want to be able to implement systems that achieve certain goals, but at the best possible cost. And so I tell both young, middle-aged, and old engineers that if you're not saving your company money, then you're of no benefit to that company. So the production and delivery of electricity could have been done if, using any technology, doing it anyway, having however many lines and cables that you feel like, if cost was not a factor. But our objective must always be, and in looking at this whole generation planning and management, one of our primary objectives is to ensure that the energy is delivered to the customer at the most economic cost. And that is something that, as a country, we have been grappling with over time. We look at our competitors and we wonder why, the manufacturing in some countries is going, well, while we may be lagging behind, the cost of energy. may be part of that. And that is something that I am more than familiar with in terms of the efforts by the government to address this matter. So the objective, to deliver energy to your customers, but to do so safely, to do so with the acceptable quality, to do so reliably, and to do so at the most economic cost. For this particular topic, we'll be focusing primarily on the quality and the economy. All right. The safety and reliability section, I suppose we'll treat with that under protection for those who will opt to do that module. All right. So having said this, now I know that at the outset this may seem a little dated in terms of what we are able to do today. Now, note I said not readily. So we are fully aware. And is quite involved in the whole business of storage. So we can store bulk power, but I'm highlighting that it's not readily stored. All right, it's a capital intensive activity. So as we, for example, increase the number of renewables that we are putting on a grid, the issue of storage becomes important, because of course you have no sunlight at night. So when you have this fantastic solar plant, it may be able to, be supplying several megawatts when the sun is high in the sky. But a simple cloud cover can move you from near peak production to zero. It can shift rather sharply. So storage becomes a problem. But for the purpose of what we'll be dealing with today, we are saying that it's not readily stored, and therefore what is produced must be consumed or what is required by the customers must be produced at the same time by the generator. So the question is, how do we balance that? How do we determine what the customers need and how much we need to generate? All right. Now, I also mentioned the fact that the customer, remember we spoke about reliability, the customer is not overly concerned about what is happening at the utility. When they walk in and flick that switch, as I mentioned, they expect to see light. Now that is for possibly just a householder, but for the manufacturer, when he comes in and starts up his plant, he expects it to run. Now that plant may be several hundred times what demanding several hundred times what you flicking the switch at home is demanding. But regardless of the difference between the demand, the expectation of the customer remains the same. That when they want electricity, when they want electrical energy, they expect that need must be met at all times. And so from a utility standpoint, there has to be an effort to ensuring that that adequate generation is always online. Always online. All right. And so we want to have a discussion as to how do we ensure that that is the case. Yes, bearing in mind that it must be done economically. So that's the balancing act for the engineer. I mean, if cost wasn't a factor, then we know that the demand in the country is what 650 megawatts. Hey, we just ensure that we always have 1,000. But having 1,000 means that you have 350 megawatts of unused capacity. That unused capacity has to be paid for. And the only way to pay for it would be to go to the customer. So the question is, what is that middle ground, and how do we arrive at that middle ground in meeting the demand? Yes? So it's not an exact science. We can't dictate to the customers what they should be demanding. Yes. So the total load demand cannot be accurately predetermined. We can't say that in the next 5 minutes, this is what will be demanded, because the utility cannot be telling customers when to use what. I mean, they can encourage it, but they can't really dictate it. But based on observation, based on what would have been seen by the utility annually, monthly, and daily, what they would have seen over time, they can have established demand patterns, right? And by virtue of those patterns, be able to provide the generation to meet that demand. So we have what we refer to as load profiles. We have daily load profiles, which provides information that will assist in the operation and planning for utilities. So there's historical data, right? And that historical data is used to inform current operation. Okay. So within this engineering space, and to meet the objective, it means that we'll have to do some forecasting of demand, and that forecasting will be based on short, medium, and long-term planning. So yes, there are some economics that we'll have to look at in this particular topic. Right? So from a long-term standpoint, I was going to say the utility, which is usually the case. The utility will do their forecasting for up to 30 years. That has been the case here on Jamaica for years. That, however, changed back in 2015 with the new Electricity Act, where instead of the utility company, which in our setting would have the JPSCo, instead of the utility company doing the long-term forecasting of our energy needs, that has now transitioned to being the responsibility of the government through the Ministry of Energy. All right, Ministry of Science, Energy, and Technology. So the government has now produced what is known as the Integrated Resource Plan, or IRP. That IRP was made public in February 2020. All right, so it was made public this year, okay? And it is looking on the generation plan for the country over the next 20 years. Interestingly, the plan was due for publication in 2018. So the plan covers up to 2038 and not 2040, right? So it's a 20-year plan looking at various inputs in terms of the demand on the system. It looks also at the age of the generating units. I submit to you that even since the 1980s, we have been talking about the B6 unit, and the B6 was one of the older units back then. In 2020, the B6 unit is still in operation. And so units like that will be removed from the system over time, yes? And as part of that long-term plan, we have to then look and see how will that impact the operation of the grid, and what would be the planning horizon to facilitate replacement of generation for the removal of the B6. So those are aspects of this long-term forecasting that is used. So as we seek to expand the system, as of course, financial planning, things have changed in the world. Well, yes, I'm trying not to mention COVID, but when we did that IRP, in terms of the financial sector, there was money available. But the question is, how would the financial markets be reacting today, given that there has been this massive slowdown in business? How will that change going forward? So we need that 20, 30 years in terms of long-term planning to look at how the system is going to change or needs to change in a major way. Now, that is on the long-term side, yes? Because of course, you don't just get up overnight and decide that you're going to change a generator. You don't just get up overnight and decide that you need to expand your transmission system or to, extend your distribution system. This also takes into consideration things like, developments. So we're talking about Bernard Lodge expansion. The question is, is the grid up to scratch to handle that? And based on where we are now, that would be part of the long-term plan. For short and medium term, these forecasting usually look from hourly, yes, to several days.
Could you just go back for a quick second?
Why is that important? In terms of the dispatch of generation, and we will highlight that with one of the diagrams that I have already sent to you. The operation of the grid within a day is significant. The difference in operation is significant. So what we see as a demand on a Tuesday will be completely different from what we will see on a Sunday. And so in terms of the historical data and forecasting in terms of which units you need to be bringing on stream when is very important. On the medium term forecasts, again, we can be looking at hourly up to several months. This medium term forecasting helps in the planning of maintenance activities. At what point in the year can a utility decide that it needs to remove a major generating unit for maintenance? Because of course the units have to be maintained, if they are going to not only work properly, but also if we are going to get the full benefit from them. So my maintenance schedule is going to be dictated by my medium-term plan. A lot of the maintenance will take place around the March, April, May, because that is sort of the low demand period. But you certainly would not want to be taking out units during the summer for maintenance, because that's one of our major peak periods as far as demand is concerned. Similarly, you wouldn't want to be taking it out November, December, or should I say November through to about February, March, early March, because that again is our winter tourist season. Heavy demand, all right? On the summer side, it's really from locals in terms of the increased air conditioning load, etc. So forecasting is important. So for short and medium term, we're looking at operational planning, whether on seasonally or daily. Yes, Ms. Michael.
Good afternoon, sir. You're breaking up.
Go ahead.
I can hardly hear you. You're breaking up.
Is any better?
Yes, sir.
Okay, I apologize. I'm currently at youth. I opted to deliver the lecture from UTech today, so internet
Oh,
may,
okay, sir.
sorry about that. All right. So the short term and medium term, as we said, these plans are used for to guide operation. So which units are we going to be bringing on at a particular time on a particular day? In terms of, you know, major maintenance, we're going to be looking at our medium-term plan. All right. Okay. Now, there are things that, as I mentioned, there are some factors that will affect our forecasting. I mentioned historical patterns already. And by that, I'm talking about things like summer. You know that you would not want to carry out maintenance during the summer, because during the summer you have that high demand, because we you know, where we live, the place is hot. So during that time, you know, the AC loading, even from a residential standpoint, is going to increase significantly. You get to that point, you just can't bear the heat anymore. You're going to get an AC. And historically, again, I come back to the fact that during that Easter period, yes, is usually when you see maintenance activities taking place, or during the September, October period. That's another low period for the system. All right. Come back to temperature. You may just have a period of intense heat, you know, even during what would have been traditionally considered to be a cool month. I mean, I think it was last Saturday was just extremely hot. Yes. So these things will throw your forecasting off. All right. Now, it's not a science, but of course we have to use the available data in terms of our forecasting. So there's always going to be question regarding its accuracy. All right. So the decisions regarding economic scheduling of our generating units or plants, how I go about when do I purchase fuel, because again, coming back to what I said at the beginning, if we are not able to facilitate savings, then our purpose as engineers will come into question. Now, if money was not an issue, I could have the company set up 50 storage facilities, fuel storage facilities, but that's a waste of money. So in terms of my forecasting, I know how the units work, understanding the full operation. I may be able to run the same generating units quite efficiently, knowing and understanding the delivery of fuel. I can do that using two or three facilities for storing fuel. Yeah. While the other man down the road, because he's not taking the engineering approach, does require the 50. So the question is, my operation would obviously be more efficient and more less costly. All right. Coming back to the long-term planning, or just part of the whole planning activity, yes, procurement of additional generating facilities. We have to understand how our load operates and recognize the economic impact that it will have on our operation. Okay. I'll pause here for a little. Any questions? Okay. So, as I mentioned briefly, I had sent you some pictures of to support this lecture, because of course you wouldn't have been able to draw this while I speak. So in the I think reading material section on the Schoology, I uploaded these photos earlier today. All right, so let's talk about what we have before us. And let me just make the disclaimer. This demand curve, it's a daily demand curve. It was for back in, I think, about 2004. Okay. If you know, the peak demand here is less than 5, it's just under 500, somewhere there. All right. We're about 650 going 700 now, 640, 650, 700. Okay, so this is our demand curve. Question is, what does it tell us about how we operate? Now, for this demand curve, we have the time here. So we know the time of day that things are happening, right? With that time of day, what we see is that, technically speaking, we just start, most of us just start going to bed there. So that's when we have the lowest demand. Yes. So all the night noises that we are struggling with continues until about 3 o'clock, them start going in bed. But anyway, that, I suppose COVID has addressed that part of things. What you can see here, however, at about 6 o'clock, right, at about 6 a.m. is when the country starts waking up. So at 6 o'clock, we start waking up. This is the period now when persons are getting ready to go to work, school, etc. And that system demand increases. What you also see is that at about 10 o'clock, right, about 10 o'clock, let me try and get that a little straighter. At about 10, right, we see that the demand really starts to pick up. 9, 10. What this is really highlighting here for us is the commercial. All right, so commercial and industrial starts to kick in. And at that point, we now see that throughout the day, it is more or less steady. So we almost get a flattening of the curve because everybody's at work, the factories are operating, the stores are open, you know, everybody using power at that time. If you note, however, at about 4:35 is when we start seeing the decline. All right, so now facilities are shutting down, business places closing, people getting ready to go home. And so we get that dip. We get that dip. All right? So we get that dip at that point. However, at 7 o'clock, we start to see the increase again. And there are a couple of things that will result in that increase. Among them would be that, one, street lights begin to come on. So this is 6:30, place getting dark, street lights coming on. And by the way, that's one of the biggest customers for the utility company, right? Street lighting. So that increases significantly. Persons are getting home, they are turning on, and you know, so they start using energy from home again. But as I said, the major part of that increased demand is really as a result of street lighting. And then from that, you know, we are seeing here 7:30, that's prime time. News, people turning on TVs, and you know, that type of activity. And then of course, we see that as persons start to retire to bed from 9 o'clock. I know that I'm speaking to a constituent that you all don't go to bed until 1 a.m. But anyway, for us normal folks who start going to bed from 9 and children retiring, okay, you start seeing the demand getting lower. And with that lower demand, we see that it then at 10:30 kind of flattens out, picks up at about the same place. At 12 a.m., we continue seeing that lowering. All right? Any questions with this? Any questions? Crystal clear? All right, excellent. Now, what we are showing here, remember I said that a day makes a big difference. What we are showing here is just how the demand will change depending on the day of the week it is. So we have here up top where this up top there, those curves represent your Friday and your Thursday and your Monday, right? These are all weekdays. So people going to work, factories running, stores, et cetera, et cetera, et cetera. So the demand is higher during that period for those curves, okay? Now I want you to note that over here and over here, yes, regardless of the day of the week, the curves are more or less bunched up, right? Now, I want to just show you a couple of things so that highlight a couple of things. Now I have to take note of, for example, the New Year's Eve curve. All right, so when I look at the New Year's Eve curve, the New Year's Eve curve is this one at the bottom here. All right, note that it is lower than a Sunday. It's below the Sunday. So New Year's Day, I said New Year's Eve. Anyway, New Year's Day. What that is telling you is that in terms of activities, it is more quiet than a Sunday, because you still have a couple places of business opening on a Sunday, right? You still have persons going out to church and other activities. So you still have some activities going on a Sunday. But when it comes to New Year's Day, most places are closed. And so you're going to see that the demand during that day period is lower than even on the Sunday. But I want you to look at the other end, which is over here. Right? At that end, we know that the night activity for New Year's Eve, so coming into New Year's Day, yes, New Year's Eve, we see that the demand is quite significant. And we know that that is as a result of an increase in intensity in nighttime activities, New Year's Eve celebrations. So you have persons at New Year's Eve parties, you have persons at church coming into that day. So we are seeing it reflected in our social activities, at this end. All right? So what I'm trying to highlight is that what we are seeing here is really representing our social activities as a people, right? Highlighted there by what we are seeing for New Year's. Now, if you look on the Monday, remember now, the Monday is the orange. So what we are doing, we are coming into Monday from Sunday. And you know that the Monday is at the bottom. Yes? Because Sunday night is not typically, maybe I'm just dating myself even more, but it's not usually the party night. So you'll find that the demand for that Sunday night into Monday would be low, right? So again, just highlighting socially how we behave, all right? Well, night creatures, really. Yeah, so the demand curve, and the point I want to make here from an engineering standpoint is that by looking at the demand curve, the utility would be able to make an informed decision as to which generating units and plants need to be in operation to meet these demands, because they would have had this historical perspective in terms of how we behave, how we use energy, and thereby be able to make the necessary provisions. All right? Any questions? Okay, now, a couple of things we had shown. And note, we identify here the spinning reserve. Now, the blue line, this line here, represents the generating capacity, which is online. All right? So the capacity of the generators that's online is represented here. All right, so we get some step changes. All that means is that you're adding new generation. Over here, you're taking off generation because people going home. Here, you're adding generation. And then you start take it off as the demand falls. But at all times, the generation that is online will be greater than the demand. So the demand or the system load will always be less than what is online. The online, the difference between the demand and what is online, we refer to it as the spinning reserve. All right? So that's what we want to get into. So here we're talking about the spinning reserve. And that, as I said earlier, is the difference between what is online, yes, and the demand. So the capacity that is online, if we take away the demand from that, we'll get the spinning reserve. Now, that spinning reserve allows you to facilitate any sudden increase in demand. Because remember, as I said earlier, as a utility, you can't dictate to the customer when they should demand or when they should be using the electrical energy. I put in a caveat, however, because there are some customers who need to communicate with the utility when they are going to, start up their facilities. And these are usually very large industrial customers. That may be changing now because many of these large industrial customers have opted to generate their own electricity. All right, but that's another matter. For the purposes of the utility company, there are some customers who need to communicate with the utility regarding their intention to put into operation some of their equipment. All right. The extent to which the generators can respond to the change in demand will be dependent on their own operating capabilities. Right? So in terms of how fast they can ramp up, meaning take on additional load quickly, that will dictate whether or not the system can adequately respond. The other flip side, because remember, you always want to have generation. Yes, you want to always have generation greater than demand. Now, whilst demand, the demand by individual customers may not be, or should I say, is certainly not as significant as the possibility of losing a generator. Right? You can lose a generator for any reason, yes, for several reasons. It could even be human error. Right? Now, if you lose a generator, you want to have that margin, yes, to ensure that should that generator be lost, the total generation on the system will still be higher than the total demand. There was a rule of thumb which says that no one generator should serve more than 10% of the total system demand. And then the flip side is that the spinning reserve must be greater than 10%. In Jamaica, I think we are using about 20% at a maximum point in terms of spinning reserve. But the key here is that you do not wish to have any one generating unit supplying more than 10% of the total demand. And then the flip side is that the spinning reserve, yes, should be no less than 10%. And what that is basically facilitating is that if you lose a generator, it means that you will still be able to supply your load until, of course, you get the generator either back online or you are able to bring in a new generating unit. All right. So these are some of the major considerations that will have to be made for your system. And just to highlight the point of the spinning reserve, we just look at the second picture that you have. All right. So we have our demand, and we must always have some reserve. Now you note that in this section of the demand curve, right, you see that the load is falling, but the generation remains constant. So no generation is being removed. These generators, we refer to them as base load generators. All right? And these generators are never taken offline. They remain online 24/7, right, until, of course, you need to maintain them. And there are several reasons for this. These generators, one, it will take a significantly long time, not only to remove them from the system, but also to bring them back on the system. So if you shut them down, if you shut down these generators, it will take a long time for them to completely shut down. Let me give you an example. A steam unit. Steam is used to drive these units. Now, even if I take the generator off the system, there is still the energy from the steam that is in the system, right? And that energy needs to be dissipated. So the unit is going to take time to cool down, to properly shut down. So there is a long time for shutdown of such a unit. The reverse is also true. I don't know, when you put on the kettle, and if you're standing there looking at it, waiting for it to boil, it takes forever. The same is true for your steam unit. For you to get a steam unit back online, it may take you up to 6 to 9 hours, because you still have to boil the water, you still have to produce the steam. So depending on where you're coming from, yes, it's going to take time to get these units back online. So it takes time to shut them down properly, and it takes time to bring them back online. And that will help you, because I'm sure, when you come to university and you go back home, for those who are from other areas, when you go back home, the questions, You know, you tell them you did engineering, they're going to be throwing every technical question at you. So I'll help you with answering one of them. Where we have an all-island blackout. You know, this may have been the result of some fault or the other, whatever the reason. But we have an all-island blackout. The generators are there, but still, some parts of the country will get back power almost immediately, but then you're out of power for 3-4 hours. Why? I mean, it's just that the generators trip. What I just explained in terms of these units is precisely the reason why it's going to take time to bring the system back up to in terms of full operation. Of course, that also depends on the time of day that the blackout occurs. All right? So it takes time to shut the units down. It takes time to bring them back online. And so you have that massive outage. It's going to take time to get these generating units back up and running. All right, is that clear? Is that clear?
Yes, sir.
Yes, sir. Quick question, sir. Sir, are these systems manually put online or activated, sir?
All right. In terms of getting the systems back online, there is direct input from the operators. So you have the plant managers who will be in contact with the system operators in terms of getting the units back online. There are some operations that are that are done automatically, but to get a unit, put a unit online, that requires input from an individual. All right. So,
okay, sir.
yes.
Sorry to cut this. But you mentioned something about an automatic part of the system. So is there like some parts of the system being automatic? So my question is, sir, so let's say an event where there's an sudden peak in the power demand, sir, is there like a system in place that generator could kick in automatically to compensate for any overload or anything like that, sir?
All right. Now, in terms of overloads, what you're gonna find happening is that if you get to a point where the system becomes overloaded, yes. So let us say, and let me back up a bit. The overload will not come primarily as a result of a customer coming online. So let's get that clear, all right? The overload is going to come primarily based on you losing generation. All right, because if you have a very large customer who needs to come online, as I mentioned before, there would be communication between them and the utility. So you're not gonna get the overload as resulting from somebody coming online. Now, when you lose a generator, what will happen is that if the system becomes unbalanced, meaning that there's a higher demand than what is being generated, the other generators in the system are going to respond. Unfortunately, their response will be for them to also withdraw from the system because they do have overload protection. So in many instances, as a matter of fact, and now that I'm thinking about it, maybe I should get access to some of these and let you have a read. One of the reports from one of the fairly recent all-island blackouts that we had occurred because the fault which happened all the way in the west, I think it happened in Trelawney, if my memory serves me right. resulted in a generator pulling out of the system because of the fault. Now, having pulled out, it immediately caused the other generators that were left to be overloaded. And those generators, based on the protection systems that were in place, also pulled out from the system. So the entire system ended up collapsing. So the short answer to your question is that no, there will be no automatic trigger for a generator to come online. That is something that needs to be watched by persons at system control. Yes. And so if you go to system control, then you would see these guys who, well, if you don't know better, you think they are just having fun and sitting down looking at these big screens. Part of the idea is that they must be monitoring what the load is like on the system and what the generation is like. They will make the necessary communication with a particular plant manager or the operators to start getting units online. So there is a constant monitoring of the system to ensure that the balance is maintained. Now, the automation I spoke to occurs, for example, and I know I'm touching a little on protection. You may have a fault on the system, and you have a recloser where, depending on the fault, it will seek to reconnect the system. If the fault was what we refer to as an incipient fault, meaning that it was just a momentary fault, in reconnecting the system, if the fault had been cleared, then the system would just continue operating as if nothing happened. All right, so the automation I mentioned was really speaking to that, not from the generation side of things. All right.
Okay, thank you, sir.
You're welcome. So we talk about reserve capacity, and based on even the question that was just asked, we have to then look at the generators and determine which units can come onto the system in the shortest possible time. So if we're seeing that we're having an issue with load, yes, then we may want what we call it quick start units, yes, that can be up and running in 5 minutes. There are other units that we may want to be bringing online. That's going to take a little time. So, of course, we will allow that to happen. And then there are, of course, systems that, we use them when available. And that is what is now happening with many of the renewable systems. And persons, for example, in central Jamaica, Manchester, some parts of St. Elizabeth, up to last year, the year before, they were having frequent power cuts, and this was in part due to the renewables that were on the system, because you may have a heavy gust of wind right now, and you may have good wind right now, and in 5 minutes you have none. You may have 18, 20 megawatts of solar, and in a couple of seconds, it is down to 5 megawatts, because you have a nice big fluffy cloud that covers the plant. Now, how do we address that? We address it in part by having storage, which is what the utility has opted to do. And so those customers should be, better served today. But of course, you'll be doing the impact of renewables as an assignment, so you get a chance to read it. Now, reserve, we can classify it as either hot or cold. Now, remember I just said that you have units that can come on the system within 3 or 5 minutes. So it means therefore that these units would be off and they'll be sitting down, ready to be engaged when necessary. But there are also units that are on the system, they're operating, but I would say they are spinning. We also say that they're hot, meaning that they are in operation, right? So the hot spinning reserve means that they are connected to the system, they're in operation, and then if you have significant demand or significant growth in the demand, these units will be able to supply the additional load. The cold reserve would be units that are sitting down, they are off, they are not connected. And when I say not connected, I just mean that they are not supplying anything, yes? And they are off, but when required, they can be quickly added to the system. Okay? So from a load standpoint,
Sir, can I go back for 2 seconds, please, sir? Thank you, sir.
all right. So from a load standpoint, we talk about base load, peak load, and intermediate loads. So base load is that load that the system will not go below. All right? So it never falls below a certain value. What we showed earlier, it would have been about 350 for the last one, for what we showed with the load demand curves, right? So your base load, the value never falls below this level. And it is fed 100% of the time. The peak load, right? So if we talk about peak load, we're talking about that. So it does peaks for a short time, right? Your peak load occurs for a small percentage of the total time, and then your intermediate load is between that. So for your intermediate load, we're talking about, yes, your base load would be here, so it would never fall below, in this instance, 325 thereabout, right? 340. Right?
Excuse me, sir.
Yeah.
In regards to understanding the slack generators, I was wondering in what way would your slack
Understanding the what?
you have a slack bus, and by having a slack bus, you'd have a slack generator connected to it. I want to understand how you would dispatch or that kind of a unit, or what kind of loads would it seek to load demand it would be seek to meet.
All right, remember that your generators are not looking at individual loads. That's the first thing you need to note, right? So your generator is not looking at individual loads. They are looking at the system load. In terms of your slack generator or your swing bus, your swing generator, one of the main purposes of your slack, and the name really speaks to what it's there for. It's really to provide voltage stability. And to do that, your slack generator is going to produce additional megavars into the system. Because at your slack bus, you want to maintain that 1 at angle 0. So if the demand is such that you're moving away from your 1 at angle 0 at your slack, and again, remember your slack is your reference point, right? To do that, it's going to export more VARs into the system. So that's the primary reason for your slack. So it's not, It's not looking per se at any individual load, and to say that we dispatch the slack would be incorrect, because the slack has to be constantly in operation, because all other voltages within the system are referenced to the slack bus. As a matter of fact, you remember in Networks 1, when we were doing nodal analysis, that reference bus that we always talk about, or I'm sorry, that reference node, not bus, that we always talk about, would be like a slack bus. Because all the node voltages, all the voltages within the system, all the bus voltages within the system are given relative to the slack. So the generator at that bus really provides voltage stability.
Okay, sir. Thank you very much.
Okay, Mr. Banner. All right, so we talk about the load, but we also can speak to the generators. So you have your base power generators, and I mentioned those earlier, operate at all times, 24/7, until we have to maintain 1 or 2. All right? Intermediate, respond relatively quickly, yes. And then your peak units, these now you need to be able to start them quickly, get them on the system quickly, and they can come off just as fast. Now, folks, when you start a generator, it costs money. So even before it delivers 1 megawatt of energy, yes, it costs. So, and not only does it cost to start it up, it costs to shut it down. So keep that in mind. All right. So in referring to the generating units, as I said, you have the base, you have the intermediate, and you have the peak. And I've given you the plot for the load. Give me the plot for the load. All right. So that's in the sorry. Oh, that's what is technology eating today. I've sent this in the figures earlier. So you have your base load, and this is just showing you the duration in terms of it being on the system. All right. No. Any other questions? Now we want to transition a little now and talk a little about some of the economics. All right. Now we're just going to touch it briefly and then yeah. So one of the terms we're going to be using a lot here is economic load dispatch. All right. Now, on the surface, that may sound a bit as if I'm contradicting myself, because I just said that we do not assign individual loads to generators. However, it's not the case. What we're saying is that you have a total system demand. So you have a total system load. What you're trying to do is to distribute that load among the units that are already online. So I mean, it's not that the generators at Hunts Bay will be picking up the loads, of Spanish Town Road. No. The loads right across the island are shared among the generators that are on the system. And they are shared in such a way to ensure that the cost is minimized. Because depending on which unit and how much load a particular unit is carrying, then it's going to cost you a certain amount. Right? Because the units in terms of the operation, the cost of the fuel that they're going to be using, yes, that's a consideration. So you have to think about cost of fuel. The age of the unit, the newer the unit, I suppose, the more efficient. Not always the case, sometimes the engines need to work themselves in. But generally speaking, newer units will be more efficient. You may also want to be controlling the amount of greenhouse gas that is produced. So in terms of that consideration, you want to also manage, or you want to put that as part of the cost function for your generator. So economic load dispatch, simply put, is how we distribute the load among the units which are already on the system. We want to compare that, however, to unit commitment. Unit commitment, on the other hand, is that process of determining the sequence of startup and shutdown of generating units to minimize overall production costs. And remember, I said earlier that these costs include both the startup and the shutdown costs. So I hope we understand the difference between the two. One is, how do I share the loads among these generating units that are already online? And the commitment is, okay, which unit do I bring online when? Both, however, are with the view of reducing cost. Because we said it at the beginning. We want to get power to the customer, but at the lowest cost possible. All right. So let us use as a rule, and now talking about unit commitment. Because remember, we want to put on the load, the generators at a particular time. Now, base load is supplied using steam. Yes. And the steam can, as we know, have it. The steam can be produced using LNG or diesel. All right. So that's one option. The LNG / diesel is also used for the combined cycle plant in Montego Bay. That combined cycle plant utilizes it now utilizes LNG to drive the engines, and then the exhaust of the engines is collected and used to produce steam for the third turbine. All right. So that would be our base load. And I've also indicated your hydro units, because the hydro units that we use in Jamaica at present are what we refer to as run off the river units. In other jurisdictions where hydro is used, in many instances, it is used as a peak generator because it uses what we refer to as pumped storage or high dammed storage. So where you have a dam where you can release the water when needed to drive your hydro plants, then those plants or those units are used to address peak demands, because with those facilities you can get the generator operating within minutes. The run of the river, however, is that you're just backing up the water and allow it to flow steadily and driving the generator. So in our case, we use hydro as part of our base load. So however, whatever the output of our hydro, the utility will take it. Your intermediate supplied by a mixture of steam and diesel, and then for your peak, using primarily gas turbines, which is really your there's a nomenclature issue in Jamaica. When we talk about gas turbines or gas plants in other jurisdictions, we're really talking about natural gas, right? And that natural gas is really used to produce steam. So, but here we're talking about internal combustion engines, all right? Or we use the term gas turbines, okay? So it could be a diesel plant, or as we are now changing all things, could be an LNG plant or unit. All right. So in terms of generation, we say hydro at the bottom, they are quite steady, right? It is not impacted by time. Then we have steam. So what you have is that it would not go below that value at any time, because of what we have been experiencing, with the units that are now in the system. We are now running some of our base load. We are now running some of our base load based on diesel plants. Now, I have a dual role here, because I have to tell the truth as a teacher, but at the same time I understand that there are other constraints in the system. But the bottom line is really the fact that we have to we have this IPP charges on our bill. What it is saying is that whatever is used to produce the electricity that you consume, the customer pays for it. In some other jurisdictions, what you do have is that there's a fixed price for electricity. It is then left up to the generator to adjust his operation if he wants to continue making a profit. In our instance, whatever the cost of production of electricity, month to month, you see it on your bill. Well, I know many of you don't pay electricity bill, but you see that on your fuel and IPP charges. All right. So this would be the generation dispatch. All right. Okay, we just have a couple more slides to go for today. Not a couple, about 10 more. All right. This is forgive me, but I totally forgot the country that I took this from, but it's somewhere in Europe. And what you're seeing is that the nuclear, that's constant, doesn't change. Similarly, coal, because you really can't shut down a coal plant per se. Yes? So it runs continually. Continuously rather. Similarly to the nuclear. For the hydro, based on what we have here, that would suggest run of the river. Yes. And then for natural gas, that we have it up there. Note, there's nothing called diesel and things. Right? And then of course they are what this green is showing is how the demand is offset by the wind energy. Because for wind in particular, you take it as it is produced. So there's no plan. There's no planned dispatch of wind. Even though if you know there are certain patterns. For example, we can basically determine what the type of output would be with respect to our wind regime here in Jamaica. We know that over time, right? So to an extent we can dispatch it, but the common literature today says that we cannot dispatch wind energy, right? And yeah, it's understandable. And then of course you have your peakers, and note those peakers can be diesel, but in many of these instances, it is hydro. So it's pumped hydro. Yes. And that pumped hydro is something that we need to be exploring here in Jamaica. So that would be an excellent project for someone to be looking at that capacity, look at the amount of energy that goes unconsumed during the day when you have all these wind facilities, peaking their output, and then, so this would be a good area of research. Anyway, so coming back to the costs, which I mentioned earlier, startup cost, you're gonna use some energy to bring the unit online, even though you're not supplying anything. So you're not supplying anything to the system, but by virtue of the fact that you start the unit, you're going to use some energy. All right. Shutdown costs. Maintain auxiliary equipment while the unit is cooling down. All right. So you are going to be expending energy. Yes. Because you have to be monitoring the unit while it is cooling down. It's not like I know I use the kettle in our first lecture to illustrate the production of steam, but we can't just now take the kettle off of the fire and just put it down. It doesn't work like that, right? We still have to monitor the equipment. There are some support systems that would be involved in that. And that will have to be monitored while cooling down. And again, that costs money. All right? So we can't just willy-nilly. So in deciding, and this is the key point, in deciding which units you're going to use as your peak units, you have to give consideration as to what it will cost you to bring it on, what it will cost you to take it off. All right? All right. Now, unit commitment on the other hand. Unit commitment on the other hand. And by the way, the startup and shutdown costs also impact the economic dispatch. And that is built into the math of things. All right. So we refer to these as the fixed cost component. So when you're generating 0 megawatts, there will also be a cost per hour for the operation of these units. And I highlight that when we start doing the math that's associated with this topic. All right. For unit commitment, yes, we want to be looking at the best units to supply the forecasted load. One would have to take into account the scheduling of different types of units. So we're looking at what's used to operate them, the fuel, the personnel. Yes. So we're looking at the units, we're looking at how they operate, we're looking at what needs to be used, what needs to be put in place for their operation. Yes. Who needs to be there? The people, the personnel that needs to be there. All of these things will play into the unit. All right. So in summary, some of the things that you need to consider for unit commitment. All right. Different efficiencies, the different fuel types. Yes. Just their economic operation. How long does it take to get the unit online? How long does it take to take it off? What is the ability of the unit to take on load quickly? Yes, that's what we mean by the ramp rates. How would it behave in taking on load quickly? For those of us who may have used standby generators, you turn on your generator, and it is fine while you're running the bulbs and some other items like that. But immediately as you turn on the iron, you hear the generator dips in terms of the sound, and then it picks up. So the demand, the significant demand of that iron, a 1 kilowatt, 1.5 kilowatts, it's reflected in the generating plant. All right. All right. We need to take note of what reserve margin are we working with. So in other words, as part of the unit commitment, the question is, how many units or which units do I need to bring online given the margin that I'm working with? Remember, I spoke to you earlier about the rule of thumb of 10%. But in the current scheme of things, we may be asking for 28%. So at 20%. So you know that you have to have that 20% given whatever variables are exist in your system. You may go up to 20%. Right? We consider system security, and that's something that we'll deal with from a protection standpoint. The constraints of your thermal unit, because there are constraints. As a matter of fact, and we'll highlight it later on when we start to do the math. Just by turning on the unit, although I said that it costs money without supplying a single megawatt, the other truth is that in turning on some units, it will produce a minimum amount. So there's a minimum amount that will produce just by virtue of the unit being on. So that's part of the constraint. At the other end, there's a maximum amount that it can produce. All right? So there are operational constraints that you'll be working with. Minimum, maximum. fuel, margin you're working with, the economic operation, the ramp rate, uptime, downtime, yes. So for thermal units, you have a minimum uptime. Right? For those, for example, a good example would be the timer that you have on some vehicles. You switch on the vehicle. Once the engine starts, you turn it on, it continues to cool down, you know, for those turbos. It's gonna take some time. You can't, it will not just shut down immediately. Minimum downtime. Remember, I spoke to you about the fact that if you have that oil island blackout and all the generators which were working came off the system, you can't just throw them back on the system immediately. Especially for the steam units, there is a minimum time that you have to allow the units to cool down before you can put them back on the system. Okay? So these are considerations that you'd have to do as far as unit commitment is concerned. Fuel constraints. The amount is going to use, the fact that, you know, some operational features, you know, it just have to use off a particular amount of fuel before you can take it off the line. These are constraints built into units. And so when you get to the point where you have to make decisions about what sort of generating facilities needs to be purchased, not necessarily for the utility company, but you may very well be working with a small company and you need to start giving thought to providing backup generation. You know, these are some of the considerations that you have to give to what you will purchase.
So, sir,
yes.
Who are the persons who make these decisions, as in their position in the company? Would they be like the plant managers or, I don't know?
Well, ultimately, it will have to be done. The go-ahead will come from the executives in the company, but they will have to do so based on the information that is provided to them by you, the engineer. You see, they will deal with the dollars and cents, but that dollars and cents must be informed by technical rigor. So if you are hoping to get away, I'm sorry.
No, sir, it wasn't really a matter of get away. It was just, you know, for a better understanding.
Yeah, okay. So coming back to the power system, I mentioned here the whole business of cogeneration. This is something that that Jamaica was looking at, you know, optimistically a few years ago. That seemed to have gone out the window for the time being. But, you know, so if you change jurisdiction and, for example, working in a you know, a frigid place, you know, we are found everywhere. All right. You need to understand that one of the considerations for a generating unit may be that it is not only providing electricity, but also providing heating. All right. You may choose that unit or a particular unit because you want the steam from it to be part of a processing plant. You know, so those are considerations that as the engineer you would make. And then you have to be clear in your mind about who you have available. If you don't have enough persons to attend to it, then, you know, although I've put it here as just numbers of persons, but you want to ensure that you have the right quality of people to deal with it. So whilst you may not all be, skipping towards power engineering, the fact is, I don't know if you all do okay, I forgot the name of it. Fluids or mechanical technology. Is that a compulsory module for you?
No, sir, only the mechanical students do it.
So it was removed from the selection, I think. So
It was
can't be
removed?
selected. Yes, sir. I don't think you can select it as an elective anymore.
Oh, that's sad. Anyway, mechanical technology. That would be pretty. Anyway, we won't carry our speed. But it would help, in making some of these decisions. Talking about load shedding. Remember I said earlier, the question was raised as to the ability of generators to be automatically dispatched. Instead of doing that, what happens is that there is a removal of generation. Because bear in mind that what may seem as an increase in load can actually be a fault, because the generators are not seeing they're not seeing the load in of itself. What they are seeing is really the current that they are supplying to the system. You with me? So if you have a fault in the system, the fault can only be supplied by the generators. The fault current can only be supplied by the generators. Now, with that is happening, then what would then be interpreted, so to speak, by the generators is that there is an increase in loading, an increase in demand. So you can have a fault in the system that could represent a load. Of course, there are other things that we have in the system that will help us to distinguish whether or not it is really a fault or just increase in load. But I'm saying this for your benefit now at this stage. So that increase in load cannot be responded to by adding generation, because you could actually be adding fuel to the fire. So the reverse is done, in that if you see an excessive load demand on the system, right, is that you seek to remove, you can remove certain customers to get the load generation balance right. And that is referred to as load shedding, and that can be done automatically or manually. The key here, and I haven't heard it being used recently, but when we have shortfalls of generation, in the past you would have heard announcements coming from the utility company indicating which blocks would have been removed from the system. Right, so certain customers were then put together. You call block A, block H, whatever, and they'll tell you which block would lose power, so you know when you'll be losing power. All right, so that man would now be call it the manual. Right, so the system control operators would remove certain customers from the system. However, you can have automatic load shedding. All right. And these will be based on the frequency or on the voltage threshold release, because a dip in the voltage or a drop in the frequency is an indication that the load is higher than the generation. All right. And once you have that imbalance, once you have that imbalance in terms of frequency, then the generator is also set to pull from the system. So you can have load shedding by virtue of that happening, or you can have the generators themselves pulling out of the system. All right? So you have the frequency issues when generation is less than your load. Okay? And that can result in the system collapsing. All right, folks. And as I said, frequency is a good indication of imbalance. Low frequency means that the unit is going to be removed from the system. So you're under frequency low threshold, all right? Will have the same effect. And then finally, some of the considerations for load shedding. Yes. You have an overload, the amount of load that you need to shed. You have frequency thresholds, time delays, priorities, and distribution. So in other words, we can shed load. Well, where you know, for those who are on campus, I'm trying to think, no, it may not affect us. I think we're on a different feed. But if you're on the same feed, for example, as the university hospital, then the likelihood of you losing power is very low. So if you want to keep power during times of emergency, I suppose you need to go live near a hospital. All right? But the utility does prioritize who loses power when the need arises. All right. So this is where we're going to end for today. I know it's a mouthful, but I hope it has helped to provide some reference point for the math that we will do when next we meet. All right. There's nothing special about the math, just that we will use it to explain a lot of what we had discussed today. All right. If you have no questions, I will just leave it the register, and then we can bid each other farewell for today. All right, Adams. Adams?
Present, sir.
Okay.
Present, sir.
Yeah, man, I heard you. Thanks. Okay. All right. Alan? Chavez? All right. Barrett? Shake? All right. Blake?
Here, sir.
Here's
Here, sir.
Hey, just run back to the computer, Miss Barron. All right. Rajay and Tevon?
Here, sir.
here, sir.
All right. Bruce? Buckley? Buckley? Burns?
Here, sir.
Campbell? Ricardo?
Here, sir.
Copley?
Here, sir.
Crosdale?
Here, sir.
Daily, also daily isn't there. Downer,
Here, sir.
Places,
Here, sir.
Dwyer,
Here, sir.
Ellis,
Here, sir.
Ferguson,
Here, sir.
Finley,
Here, sir.
Francis,
Here, sir.
Gibson,
Here, sir.
Henry,
Here,
Henry,
sir.
Hewitt,
Here, sir.
Jeffrey,
Here, sir.
Johnson,
Here, sir.
Kamika,
Here, sir.
Carr,
Here, sir.
Leon, Mason,
Here, sir.
Merchant, Montague,
Here, sir.
Norton, Phillips, Porter, Phillips,
Yes, sir.
Porter, Ramsey,
Here, sir.
Ready, Reed, Christoph,
Present, sir.
Dario,
Present, sir.
Rose,
Present, sir.
Ms. Russell,
Here, sir.
John, Shirley,
Here, sir.
Sinclair,
Here, sir.
Michael,
Here, sir.
Neff, Rajiv, Thomas, Jerome, Red, Venna,
Present, sir.
Williams, Zheng. All right, so
Sir, Shandy's here, sir. I didn't hear my name.
all right, folks, that's it. Have a good one.
All right, blessings, sir.
Yeah, man, take care.